Hello everyone, my name is Aman Gupta, and now I'll be talking about feed and ads modeling for multimedia use cases at LinkedIn. In this part of the tutorial, we'll talk about three things. One is common tech that we leverage across use cases for multimedia modeling at LinkedIn. Then we'll dive deep into feed multimedia modeling at LinkedIn, followed by ads multimedia modeling. Although multimedia artifacts like images and transcripts for videos can be used for modeling, we'll focus most of the discussion on video frame data. So let's dive deep into common tech for modeling. The goal of the common tech section is to provide video representation techniques that are leveraged for different product applications. And this signal from video content can be used in production models for both feed and ads. When we talk about video data, two things come to mind. One is the video frames, and the second is video transcript. In the earlier parts of the tutorial, we talked about how we sample videos at 1 frame per second for machine learning use cases at LinkedIn. For example, if a video is 100 seconds long, we sample 1 frame for every second of the video and create 100 frames from the video for machine learning use cases. To create a video level embedding, we first need to create embeddings for these video frames. For image frame embeddings for videos rather, we use an Inception v3 model that is pre-trained on ImageNet data. So as you can see here, for an Inception v3 model, the input is a fixed size image and the output is an 8x8x2048 embedding. For our use cases, let's assume that there are n frames per video. And for each frame, we first center crop it and resize it to the same size. And this is done because when we get videos from our members, they are of different sizes and the aspect ratios are all different. This is how we standardize the data, followed by pushing each frame through an Inception v3 pre-trained model to get a final embedding of 8x8x2048. This refers to the last but one layer of an Inception v3 network. This 8x8x2048 volume is then average pooled across the first two dimensions to get a 2048 dimensional embedding for every frame. Now, this technique of creating a 2048 or a similar size embedding for every frame is a standard technique used in many video understanding datasets and use cases. Now, when we have the frame embedding, how do we combine the different frame embeddings to create a video level embedding? The first and the easiest idea that we can use is borrowed from NLP and it's called bag of words. Let's assume a use case where a video you take frames from a video and cluster them using k-means. And let's say you already have a trained k-means model, you just want to assign each frame to the right cluster. Let's assume that for a given video, the cluster 1 gets 100 frames, and cluster 2 gets 1 frame, and cluster 3 gets 35 frames, and so on. In this particular case, we can simply divide the counts for each cluster by the total number of frames in that video to get a simple bag of word representation. So this is a specific example. Given n frames for a video, you first push them through an Inception v3 network and get these xi representations. These representations are then assigned the right clusters in a pre-trained k-means model. And for a given cluster, we simply count the number of frames in that cluster and divide by the total number of frames for a given video to get the representation of a given video for a given cluster. To summarize this technique, this is a low dimensional representation that we create using 0th order cluster statistics. And in terms of implementation details, we use roughly 8 million video frames to train this cluster model using k-means. And the frame embedding dimension is 2048. And the number of clusters can vary. And we end up choosing numbers like 30 or 50, which empirically work well for us. This is a depiction of the representation for each video aggregated across all the videos. And you can see along the x-axis, you have different clusters, and not all clusters are created the same. So some clusters end up seeing more data from videos, whereas the others don't see as much data. In our empirical experiments, we noticed that each cluster tends to represent some semantic concept. For example, one cluster might be responsible for indoor scenes, or one cluster might be representation for outdoors, and one for faces. So these clusters tend to represent some semantic concepts that might be crucial to discerning between different videos and what they consist of. Invariably, they end up being very sparse. So we talked about unsupervised bag of words. Now let's talk about some metric learning based video representations. So the first representation that we'll talk about is called collaborative deep metric learning based representations. This is a work that was published in literature in the past few years. And the idea of metric learning is not new. It's very popular for image understanding. And what you do in metric learning is embed artifacts in a metric space such that they mimic some concept of similarity. For example, LinkedIn members end up watching videos on LinkedIn feed. And if they end up co-watching two videos, we want those two videos to be close to each other in the final embedding space. Here we define co-watch to be two watches of two different videos in a very short span of time, preferably within the same LinkedIn session. So specifically in this diagram, we can see that the input to the model is a set of video features. And then we have a few fully connected layers. So we create an MLP followed by L2 normalization and a loss function that mimics metric learning. In this case, specifically, we use the triplet loss, which is very popular for image metric learning and was originally introduced for applications like person re-identification. So let's talk specifics of how we can get metric learning done for the LinkedIn use case. So as I already mentioned, that we get co-watch data from LinkedIn feed and we observe members watching two videos in the same LinkedIn session. It's also possible that a member is impressed with a video, but does not watch that video. So we create triplets out of the data, and the triplets are labeled anchor, positive, and negative. And the anchor and positive are co-watched, whereas the anchor and negative are not co-watched. So the objective here is to pull the anchor and positive closer to each other and push the negative away from the anchor such that the relative distance between the anchor and positive is lower as compared to anchor and negative. We create many millions of such triplets and then push raw features of a video through this network such that co-watched pairs end up being closer to each other and negatives are pushed away from the anchor. So you can see the triplet loss function here, and we also use a margin alpha, and this is a hyperparameter that can be tuned for a specific use case. And finally, the embedding we get is a combination of the raw content features and also co-watch information. So this can be thought of as an embedding containing both content information as well as member behavior on LinkedIn feed. We can also represent members using the CDML technique, where we look at what was served to members. We look at their watch history. So we can create these tuples of MI, VI, TI, where MI is a given member. They watch some video V at time I. And we can create this triplet set of member interactions using anchor, positive, negative, do CDML learning. And we can also create a member side embedding by looking at the entire history of what members watch. For example, if you have watched 15 videos in the last week, those 15 videos CDML representations now become a proxy for a member representation. This allows us to create member representations purely on the basis of the video content they watch. And This can be complementary to other information we use for feed and ads modeling, where we already have information about other behavior, and this can give us some content information. So we can also combine CDML and DSCMM, which was described in the theory section of the tutorial. Because CDML can take any set of raw features, theoretically, you can push any kind of video embedding through this network. So in the previous approaches, we used the unsupervised bag of words as input and learned a transformation F for CDML. We can push a richer and novel video embedding like DSCMM. And what we can do here is take a sequence of frame embeddings for a given video and learn this compositional function F of G, where G is the DSCMM. Now, both CDML and DSCMM can then be learned end-to-end on the final triplet loss objective. So this is a depiction of how we can do triplet training using CDML plus DSCMM. So here we have the anchor, positive and negative, stacked vertically. And for every video, we have n frames, and each video's frames are of d dimensions. So for example, this D can be 2048, where you get this embedding from a pre-trained Inception v3 network. And we can sample n frames per video to make sure we have the same number of frames across all the videos. This is first pushed through a DSCMM block, which then outputs a K cross D embedding for each video. Typically, D has to be the same as the D in the input, but K can vary. And typically, we have experimented with values ranging from 1 to 256. And in literature as well, similar techniques like NetVLAD use K equal to 256. So this is a fairly large and rich embedding representing the video and information contained in the video. This can then be followed by the F function of the CDML network, where you have two fully connected layers. And this results in a L-dimensional embedding for the anchor, positive, and the negative. And this can then be trained on triplet loss. So in our empirical experiments, we have found that this combination tends to yield more positive results than CDML plus unsupervised bag of words. We will discuss the specifics of the results in the forthcoming section. So just to repeat the CDML diagram with DSCMM as part of it now, you can see here that the diagram is almost exactly the same, but the triplet loss function has changed. Instead of just F, you have a composition here, F of G, and the input to G is the frames of a given video. And this is obviously a larger network because you have to train more parameters, so it takes longer to train, but ends up being a richer representation for a given video, and better metric learning can be performed on this combination. So this was about CDML and unsupervised bag of words and video representations. Now D will talk about member video affinity, other common technologies, and he'll dive deep into specific use cases for feed and ads. I will now hand over to D.